So in last lecture we talked about eigenvalues and eigenvectors. Eigenvectors, eigen is a German word which means self or my own. So जो आपका अपना होता है उसके साथ आप स्पेशल ट्रीटमेंट करते हैं. तो ये जो मैट्रिक्स के eigenvectors हैं, it gives special treatment to those vectors. It does not produce any rotation in that particular vector. It only produces scaling. In last lecture we also learned how to compute eigenvalues and corresponding eigenvectors, and then we discussed a matrix. This was a matrix, and corresponding to this matrix we had computed eigenvalues. So corresponding to this matrix we had one eigenvalue at 5 and two eigenvalues at -3, and we say that this eigenvalue has algebraic multiplicity of 2. Algebraic multiplicity of this eigenvalue -3 is 2. And then corresponding to these eigenvalues, we computed eigenvectors. Corresponding to this eigenvalue, we had one eigenvector, and corresponding to this eigenvalue, we had two eigenvectors. And we say that geometric multiplicity of this eigenvalue, denoted by small m, that is also equal to 2. Corresponding to this eigenvalue, there are two eigenvectors, so geometric multiplicity is 2. In general, this is the relation. Geometric multiplicity is always less than or equal to algebraic multiplicity. So the question that was raised over here. Geometric multiplicity is always less than or equal to this algebraic multiplicity. And the difference between the two, that is denoted by delta lambda, that is called defect of that eigenvalue. For this particular case, what was defect of this eigenvalue? 0. What was defect of this first eigenvalue? 0. So defect of an eigenvalue is defined in this way. So compute the eigenvalues, eigenvectors, and all these things for this matrix A given by, so that can be quite easily determined. Eigenvalues are the roots of this equation. So a minus lambda I is a minus lambda, so that is lambda square is equal to 0 and lambda equal to 0, and this is second order polynomial. It has two roots, so both of them are equal to 0. So what is algebraic multiplicity of this eigenvalue? 2. Corresponding to this eigenvalue, you can determine the eigenvectors. Eigenvectors are solution to this equation ax lambda I lambda x. How would you solve it? You remember the procedure. You will solve this equation, system of equations. You will write this matrix, augmented matrix, and then reduce it into echelon form, use back substitution. So all that procedure you already know. Is this matrix A minus lambda I is given by lambda is equal to 0. So A minus 0 is the same matrix A. So 0, 0, and the right hand side of the equation. This is already in echelon form, and therefore x2 is equal to 0 from the first row, and x1 can be anything. So this eigenvector is given by any value of x1 and this is an eigenvector corresponding to that eigenvalue. So what is the defect of this eigenvalue? 1. Defect is 1. The algebraic multiplicity is 2, geometric multiplicity is 1, so defect of this eigenvalue is equal to 1. So what is eigenspace? Corresponding to an eigenvalue, there exist eigenvectors, and span of those eigenvectors is called eigenspace. Corresponding to an eigenvalue, there are eigenvectors. For example, in the this last example, this matrix A was taken, and corresponding to this one, we had an eigenvalue at -3. Corresponding to this eigenvalue, we had determined two vectors, and these two vectors span a space, and that space is called eigenspace corresponding to that particular eigenvalue. Any linear combination, this is an eigenvector, this is an eigenvector, any linear combination of these two vectors will also be an eigenvector corresponding to the same eigenvalue. That is, if this vector is W, this vector is X, if W is an eigenvector of this matrix corresponding to this eigenvalue, X is also an eigenvector of this matrix corresponding to this eigenvalue, then any linear combination of these two vectors will also be an eigenvector corresponding to the same eigenvalue. So the span of these two eigenvectors is called eigenspace corresponding to this eigenvalue. Similarly, we had an eigenvalue of this matrix at lambda equal to 5, and corresponding to this eigenvalue, we had found a vector, any linear combination of this vector, that is any scalar multiple of this vector, will also be an eigenvector for this matrix corresponding to this eigenvalue. So the space spanned by this eigenvector is called eigenspace corresponding to this eigenvalue. So there was some question. Yes. So the question is, for this particular matrix, we had an eigenvector W, another eigenvector X. Both of them correspond to this eigenvalue. We have another eigenvector Y, which corresponds to this eigenvalue. So the question is, if we have a vector which is a linear combination of these, for example, three vectors, any linear combination of these three vectors, is it also an eigenvector? So answer is no. Here we can prove that if this is an eigenvector, then their linear combination will also be an eigenvector. Proof is simple. We know that A multiplied by W, if W is an eigenvector, then A multiplied by W will be equal to lambda, in this particular case -3 into W. Is that clear? Also, A multiplied by X will also be equal to -3 multiplied by X. Right? So their linear combination, that is A multiplied by C1W plus C2 X, that is equal to, so this is equal to, if take -3 common from here, so C1W plus C2X, is it visible? Right. So that is this vector which is linear combination of these two vectors is also an eigenvector corresponding to that matrix. Normalized eigenvectors. So here we have eigenvectors for a matrix. The magnitude of these eigenvectors is not equal to 1. we can normalize these eigenvectors by dividing this vector by its magnitude. Then that vector is called normalized eigenvector. So the magnitude of this eigenvector is square of this first element, square of the second element, plus square of the third element, whole square root, which is square root of 5. So this eigenvector, when normalized, becomes equal to minus 2 over square root of 5, 1 over square root of 5, and then third entry is 0. So this vector is now normalized eigenvector. Similarly, you can normalize the second eigenvector. So normalized second eigenvector is 3 over square root of 10, 0 and 1 over square root of 10. So corresponding to this particular eigenvalue for that matrix, these are the normalized eigenvectors. Few more properties of these eigenvalues and eigenvectors. Here is a theorem which states that the matrix A and A transposed have same eigenvalues. Matrix A and its transpose have same eigenvalues. Why? Because the characteristic polynomial corresponding to A and A transposed is the same. Therefore, both the matrix and its transpose have same eigenvalues. Eigenvalues of symmetric and skew symmetric matrices. Here is a theorem which states that eigenvalues of symmetric matrix are always real. Eigenvalues of a symmetric matrix are always real. And the eigenvalues of a skew symmetric matrix, these are either 0 or purely imaginary. So verify this statement for this particular matrix. This is a skew symmetric matrix. The eigenvalues can be computed easily by finding the characteristic determinant and then finding the characteristic polynomial. All of you know how to find that. A minus lambda I, this determinant equal to 0. So how you can find that? Take lambda common from here. So lambda square plus 625, that is equal to 0. We have multiplied the whole expression by negative sign, so which gives you lambda equal to 0 and lambda equal to plus minus j25, or j or iota, whatever notation is more convenient for you, you can use that. So minus lambda over here. Yes, you are right. Orthogonal matrix. Orthogonal matrix has eigenvalues So before we talk about eigenvalues of orthogonal matrix, what is an orthogonal matrix? If for a matrix A transposed is equal to A inverse, then that matrix is called orthogonal matrix. ये कह रहे थे कि for him it is more convenient A transposed into A that is equal to identity matrix. So yes, you can also write it in this way. For orthogonal matrix, if A transpose multiplied by A, that is identity matrix, then that matrix is called orthogonal matrix. And determinant of orthogonal matrix is always equal to 1 or minus 1. Determinant of an orthogonal matrix is either plus 1 or it is minus 1. So can you prove this statement? From here, determinant from this equation determinant of A transpose into A, that is equal to determinant of identity matrix, because this A transpose into A is equal to identity matrix. What is determinant of an identity matrix? 1. So determinant of this matrix is equal to determinant of A transposed into determinant of A, that is equal to 1, but determinant of A transposed is the same as determinant of this matrix A, so this is equal to determinant of A multiplied by determinant of A, which is determinant of A square, and this is equal to 1, and hence determinant of A is equal to +1 or -1. Determinant of an orthogonal matrix is either +1 or it is -1. And for an orthogonal matrix, column vectors or row vectors are orthonormal. What are orthogonal vectors? This is orthogonal matrix. What are orthogonal vectors? So what is A transposed B? And A transposed A is not equal to 0. So therefore these set of vectors are called orthogonal vectors. What are orthonormal vectors? So inner product is 0, that is these vectors are orthogonal as well as their magnitude is 1. For example, these vectors, their inner product is equal to 0 and the magnitude is equal to 1. So these vectors are called orthonormal vectors. These vectors are orthonormal. If this matrix A is orthogonal, then its column vectors as well as row vectors are orthonormal. This word orthogonal vectors and orthonormal vectors, this is clear. Orthogonal vectors are vectors which are perpendicular to each other. Orthonormal vectors are also perpendicular and they are also normalized. Their magnitude is 1.